Welcome back to my channel. In the last video or previous video, I explained first example under divide and conquer approach, that is binary search. Today in this video, I'm going to explain another example of divide and conquer approach, that is merge sort. Okay. So what is merge sort? So actually the divide and conquer approach is completely implemented in this merge sort. What is divide and conquer approach? Dividing the problem into sub-problems and solving those sub-problems individually and combining the solutions. Here we are going to show these three operations under merge sort, because merge sort is requiring all these three operations. Okay, so what do we mean by merge sort? So whenever you take elements, if you want to sort the elements by using merge sort, the aim of merge sort is dividing the problem into sub-problems. I will show you how this particular merge sort is dividing. Merge sort can divide the problem into sub-problems, and so these sub-problems can be solved individually. So after getting the individual sub-problem solutions, we are going to combine the solutions by using merge procedure. So here we are using merge sort for solving the sub-problems, and by using merge procedure for combining all the individual problem solutions. Okay, suppose if we assume the elements of the given array are a of 1, a of 2, so on, a of n. Assume, so these are the array elements, or you can write, I have already told you can write this also, a1, a2, so on, n. Any representation you can use for representing the array elements. Suppose if you take a of 1, a of 2, so on, a of n are the given array elements, n array elements. So in this case, by using merge sort, okay, the aim of merge sort is dividing the problem into sub-problems. So here division is taking place exactly at half. Half means, now take the low and high, take the low location number 1 and high location number n. Take low location number 1 and high location number n. Immediately calculate mid. So 1 plus n by 2. So this symbol is floor symbol. Suppose I have already explained in the previous video. Suppose in floor symbol, if you get division as 2.5, then it results 2 only. And suppose if you take seal, 2.5 means 3 is the resultant number. But here we are going to consider the previous integer value, which is less than the 2.5. Okay. So after calculating mid, this merge sort is dividing this entire array into two subparts. Okay, now one is from a of 1 to a of n by 2. So this is one subproblem. First subproblem, and second subproblem starts with n plus 1. A of n by 2 plus 1 to a of n. So like this, by using merge sort procedure, we can divide the given array, given problem into two subproblems exactly at mid. Okay, na? So mid is, if number of elements are n, then mid is becoming n by 2. Then the entire problem becomes two subproblems, or divided into two subproblems. One is from a of 1 to a of n by 2. Another one is from a of n by 2 plus 1 to n. Suppose if we take elements from 1 to 10, a of 1 to a of 10. Low location number is 1, high location number is 10. Low location number is 1, high location number is 10. Then 1 plus 10 by 2 is the mid. 1 plus 10 by 2 is 11 by 2, 5.5. Actually we get 5.5, but we need to take floor. So 5 only. So a of 1 to a of 5 is one subproblem. A of 5 plus 1 means a of 6 to a of 10 is another subproblem. Is it clear now? Then take this subproblem as input and apply merge sort again. Take this subproblem as input and apply merge sort again. That means we are solving these two subproblems individually. So solve this subproblem and solve this subproblem. Okay, now. So again, merge sort is applied here. If problem is larger, means if single element is there, we cannot divide it. So we need to apply merge sort procedure, divide the subproblem into subproblems, subproblem into subproblems until single element problems. We are supposed to divide subproblem into subproblems, and those subproblems are relatively larger. Then again divide that problem into subproblems, like that until getting single element problems. So if number of elements in that particular problem are only 1, then we cannot divide it. that element itself treated as a solution. That element itself treated as a solution. So MetStart ultimate aim is taking the input as original problem, and dividing that original problem in exactly at a mid. So after dividing problem into two subproblems at mid, then a of 1, if low is a of 1, a of 1 to mid becomes one subproblem, and mid plus 1 to n is becoming another subproblem. Again, MetStart, we need to apply MetStart on this first subproblem and MetStart on second subproblem. Okay, so again, the MetStart verifies whether this problem is relatively larger or not, and second problem is also verified against larger. Okay, na? If first subproblem is larger, again MetStart is applied recursively. So the MetStart will be applied recursively on all these subproblems until getting, I've already told, until getting single element problems. Once you get single element problems, each element is treated as a solution of that particular problem. Each element is treated as solution of that particular problem. So once you get all the individual problem solutions, then simply apply merge. So finally, we need to apply merge for combining all the individual problem solutions. So applying MetStart for dividing the problem into subproblems, and again if subproblems are relatively larger, again divide subproblem into subproblems, like that. If even array is containing two elements, we treat it as a relatively larger problem. Again, we need to apply MetStart procedure to get the individual element problems. Once you get individual or single element problems, each element is treated as a solution. Then finally, we can apply merge for combining merge as a procedure for combining all the individual problem solutions. So this is the basic information related to merge sort. Here I am going to take one example, and through that example I can explain what is merge sort. After that, I can also show you the tree structure format. Means by using the tree structure format, we say where this particular problem is divided into two subproblems. Again, where this particular subproblem is also divided into two subproblems, like that particular merge sort tree structure shows. Again, I can also show you merge calls related tree structure. In that merge call related tree structure, where this particular merge is happening among the elements. So through these two tree structure formats, I can show you. Through one tree structure, I can show you where how merge sort is happening on the elements, and by using another tree structure, how the merge is taking place among the elements. Now I will take one example and I will explain. So here I am taking one example with the 6 elements, and elements are 2, 10, 9, 6, 5, 4, and location numbers are 1, 2, 3, 4, 5, 6, or you can also take index numbers from 0 to 5 or 1 to 6, nothing wrong. You can take any index number, any starting number, so either 0 or 1. Then I took one as starting index number and final index number is 6. So here I am going to show tree structure format for merge sort. So initially, so what is the problem now? Low location number is 1, high location number is 6. Okay. So what is the merge sort? According to divide and conquer approach, so you divide the problem into subproblems. How this particular problem will be divided? Low location number is 1, high location number is 6. 1 plus 6 by 2 or 7 by 2. What is 7 by 2? 3.5. So 3.5 means 3 only. So original problem is divided into two subproblems at mid. That mid location number is 3. Now we got two problems. One is 1 to 3 is one problem, 4 to 6 is another problem. So initial problem 2, 10, 9 and 6, 5, 4. Like this we got. Okay na? So initially we took one subproblem. Here we applied one merge sort procedure. Okay na? So merge sort procedure divided this 1 is to 6 problem, original problem, into two subproblems now. One subproblem is 1 is to 3 means low location number 1 to high location number 3. So 3 is becoming high location number for the first subproblem, and because mid, so 1 to mid is one problem, mid plus 1 to high is another problem. Okay na? So mid is 3. So first location number to mid is one problem, mid plus 1 to high is another problem now. So 1 to mid is 3. So 1, 2, 3, mid is 3. So 2, 10, 9 is becoming one problem. Mid plus 1 means 6, 5, 4 means 4th location, 5th location and 6th location. So we represent it as 4 to 6 means range. Range we can represent by using these two. Okay na? So these two are two subproblems now. Okay na? So from the original problem, after applying merge sort one time, we got two subproblems. One subproblem is containing 1 to mid, another problem is containing mid plus 1 to high. So still this problem is relatively larger. This problem is relatively larger because these two subproblems are having more than one element. These two subproblems are having more than one element. So index numbers are 1, 2, 3, 4, 5, 6. Like this we got two subproblems. Again apply merge sort on this problem and merge sort on this problem. So apply merge sort on this problem and again merge sort on second subproblem. So apply merge sort on first subproblem and apply merge sort on second subproblem. So merge sort on first subproblem again calculates mid. So what is mid now? 1 plus 3 by 2. Mid is 1 plus 3 by 2. 4 by 2. Okay? 2 is mid. 2 is mid. That's why this merge sort divided this problem into two subproblems. One subproblem is containing 1 into 1 to 2 means 2 elements. So 2, 10 is one subproblem. And second subproblem is containing only one element. That element location number itself low, that location number itself high. That element low, location number itself low, location number itself high. Because only one index number is there, that index number is 3. Then low, high, both are treated as same number. So initially low is 1, high is 6. This number is, this particular problem is divided into 1 is to 3. Here low is 1, high is 3. Here low is 4, high is 6. So again this problem is considered for merge sort as input. Again 4 is to 6 problem is considered as input for merge sort. This merge sort divided this problem into two subproblems. One is containing index number 1 to 2. So low is 1, high is 2. Another problem is containing 3 is to 3 means only one element is there. That element index number itself low, that element index number itself high. We cannot divide it. We cannot apply merge sort on this because we got third problem solution. Still, this problem is relatively larger because that problem has more than one element. Then consider this that problem with index numbers 1 and 2. Okay, na? So index number, low index number is 1, highest and high index number is 2. Again, if you apply merge sort on this. If you apply merge sort on this, immediately merge sort calculates mid between these two. So low is 1, high is 2. 1 plus 2 by 2. Answer is 3 by 2. 3 by 2 means 1.5. But low, here we are going to take floor. So that's why 2 becomes one subproblem, 10 becomes another subproblem, 9 is becoming another subproblem. Anyway, right side part is there. Right side part is 654. 654. Okay, na? So this problem is relatively larger. That's why we applied merge sort on this. This merge sort problem divided two element problem into single element problems. So one problem is containing one element with index number 1. Another problem is containing one element with index number 2. So that index number 1 itself low, that index number 1 itself high. Here also the index number 2 itself low, that index number 2 itself high. Okay, na? So like that apply the same procedure, same merge sort procedure on right side subproblem. So right side subproblem index numbers are 4, 5, 6. 4 is to 6 means 4 is low location number, 6 is high index number or high location number. Whatever it may be, the index numbers, either low index or low location, high index or high location. So 4 is to 6. If we apply merge sort on 4 is to 6, means so 4th index number to 6th index number subproblem, merge sort treats that this problem is still relatively larger because it has more than one element. Again, merge sort calculates mid between these two. So 4 plus 6 by 2. 4 plus 6 by 2 is 10 by 2. 10 by 2 means 5 is the mid location number. So obviously the merge sort problem divides this problem into two subproblems. One is from low to mid, another one is from mid plus 1 to high. What is low for this problem? 4. What is mid? 5. So 4 to 5 means low to mid is one problem. Mid plus 1 to high. Mid plus 1 is 6. High is also 6. So low is to high. Low is to high. So 6 is to 6. Here only one problem is there. But still 4 is to 5 problem is relatively larger. Again merge sort required here. Merge sort is required here because our ultimate target by for applying merge sort is dividing the entire problem into some subproblems. Those subproblems should not be divisible further. So if you take element problem, if all the problems are containing single elements, then we cannot divide them further. Is it clear now? So that is the aim of merge sort. So divide the problem into subproblems. Subproblems can be divided into subproblems until reaching the subproblems in such a way that those problems cannot be divisible further. So here So 4 is to 5 is divisible because it is having more than one element. Just by applying merge sort, we get two subproblems now. One subproblem is containing one element with index number 4. Another subproblem containing one element with index number 5. So that index number itself treated as low, that index number itself treated as high. Here this index number itself treated as low, this index number itself treated as high. So initially this problem is divided into two subproblems at this location because 4 and 5 are coming to one subproblem and 6 is coming to another subproblem. We cannot divide it further. That element itself solution. Again, we need to apply merge sort one more time on this particular problem. Here this problem can be divided into 4 index number is one problem, 5 index number is one problem and 6 index number is another problem. Like this we get divisions. So this is the result of merge sort. This is the result of merge sort. So after applying merge sort completely, we get the solution of individual problems because 2 is the solution of first problem, 10 is the solution of another problem, 9 is the solution of third problem. So like that, okay, like that. Even if we see the tree structure format, where this particular problem initially started. Initially, they started with the original problem. How this particular merge sort divides the problem into sub-problems and sub-problems. Just by going through this particular tree structure, we can observe. We can know how merge sort is applied on original problem, how that particular original problem is divided into sub-problems. Just by going through this particular tree structure format, we come to know that this is the way of dividing the entire problem into smallest subproblems. Now at the leaf level, this problem is 1:1 means only one element is there. Here only one element is there. Here only one element is there. Here only one element is there. In this case also it is containing only one element. Here also only one element. So we cannot apply merge sort on these subproblems. We got 6 subproblems because there are 6 elements. And just keep on applying merge sort procedure, which leaves the subproblems with the size as one element. Like that, if number of elements are 10, we get 10 subproblems. If number of elements are n, we get n subproblems. If we divide merge sort continuously or recursively on all the subproblems, we get the problem status like this. Now we got 6 subproblem solutions. Each element in that particular subproblem is the solution of that particular subproblem. But we are not requiring solution like this. Our ultimate target is getting the solution of this entire problem. But we got all the individual problem solutions. Then by applying merge procedure, another procedure is there. Just by applying merge procedure, we can get the solution. But how this particular merge is happening? Generally, merge sort initially taken original problem as input. Initially, merge sort started at original problem. And keep on dividing the original problem into subproblems, and those subproblems are into sub-subproblems like that. So merge sort is treated as top-down approach. Then what about merge? All the solutions are available at leaf levels. All the solutions are available at bottommost level. So for calculating this problem solution, this subproblem solution, we need to combine these two elements. Okay, na? For combining these two, this is low, this is mid. Okay, na? This is low, this is high. This is low, this is high for this particular problem. But this high was the mid of this. Okay, na? This high was the mid. What is mid now? Mid equal to 1 here. What is mid here? Mid is 2 here. What is mid here? Mid is 3 here. Is it clear now? Okay, na? So by using this mid, we can reach this problem because this is the next immediate location of mid. Yes or no? Once you know low and mid, we can go to next problem also. Just by increasing mid by 1 unit, we can reach next problem. Okay, na? So that's why merge is requiring 3 pointers. Merge sort is requiring only low and high because mid calculation is requiring only low and high. Only low and high are required for calculating mid. That's why merge sort is requiring only 2 parameters. One is low, another one is high. But while combining all the subproblem solutions, the merge is requiring 3 parameters. One is low. Low is the low for the first subproblem, and mid is the last location number for the second subproblem. Okay, na? Then if you know the mid, we can get the first location number of the next subproblem, that is mid plus 1. Just by taking mid plus 1, we can reach the second subproblem, initial location, and we need high. This high is the last location number or last element of the second subproblem. So we need to know low of the first subproblem, high of the second subproblem, Just by using mid, we can identify the last element of the first subproblem and first element of the last subproblem, second subproblem. Because if we add 1 to this mid, we reach mid plus 1. Means mid plus 1 is the first element of the second subproblem. Yes or no? If we treat this as the subproblem, after dividing this subproblem into two subproblems, we get mid as 1. Mid as 1. Yes or no? Then we get one element here and one element here. So if we add if we add 1 to mid, we get second subproblem element. Or otherwise, here only two elements are there. If you observe this original problem, 1 is to 6. What is the mid of this? 3 is mid of this. Then 1 to mid becomes one subproblem. Mid plus 1 to high becomes another subproblem. Is it clear now? So for merging these two subproblem solutions, one is low required, one is required, one is required because one is the low location number of this problem, and mid is required. Mid is the last location number of the second subproblem. But no need to worry about initial location of the second subproblem, because we can get initial location of the second subproblem by adding 1, 2, 3. Then 3 plus 1 is 4. Then we can immediately reach the first element of the second subproblem. But we need high. We need high. So that's why merge is requiring 3 parameters. Merge sort is requiring only 2 parameters, because just merge sort is used for dividing the problem into subproblems. Those subproblems can be internally again divided into subproblems and so on. But for calculating division point, only 2 parameters are required. One is low of this problem and another one is high of the problem. If I add these two items and divide by 2, we get the mid. We get the mid location. So that's why merge is requiring only 2 parameters. One is low, another one is high. But merge sort is requiring 3 parameters, because we are going to combine 2 subproblem solutions. That means we need to consider all the elements in the first subproblem. We need to consider all the elements in the second subproblem. But how can we reach the second subproblem now? These two problems are obtained from its parent. So parent is 1 is to 6 for these two. Parent is 1 is to 3 for these two. So that parent is divided into 2 subproblems at mid. Okay, so if you know mid, anyway low is available at first subproblem. Just by using low and mid, we can get the entire problem of first subproblem, and by knowing high, we can get the ending point of the second subproblem. But how we can reach the starting location of the second subproblem? Just by increasing mid by 1 unit, because earlier problem is divided into 2 subproblems at mid only. We considered low to mid as one subproblem, mid plus 1 to high as another subproblem. So how can we reach lowest location number of second subproblem now? Just by adding mid to 1. Then we get mid plus 1. So like this, the merge is requiring 3 parameters. Now I am going to show you how these particular problems are divided, merged or combined each other, just by going to this particular tree structure format. Okay. So just by observing merge sort, we say that merge sort is top to bottom approach, because merge sort at the root node original problem is taken as input, and just by calculating mid at every subproblem, that particular problem is divided into 2 subproblems at mid. Low to mid becomes one subproblem and mid plus 1 to high becomes another subproblem. Like that, if we take 6 elements, those 6 element problem can be divided into like this. So irrespective of the elements, whatever the elements that are there in the array, we need not bother about those elements. Even if you take 10 elements or 20 elements, those 20 elements are 10 elements related tree structure flow is like this. Okay, now take low and high, calculate mid. So take low to mid as one subproblem and mid plus 1 as another subproblem. And again verify whether the problem is smaller problem or not. Because according to divide and conquer approach, if problem is very smallest, we get the solution directly. Otherwise, we need to divide the problem into subproblems. So here 1 is to 3 is also relatively larger. That's why we divided this problem into 2 subproblems at mid. 1 plus 3 by 2, 4. 4 by 2 is 2. So low, mid plus 1 to high. Because only one element is there. That element itself low, that element itself high. Like that 4 plus 6, 10 by 2, 5. So low is 4, mid is 5. Mid plus 1 is 6, high is also 6. So like that we divided the problem into subproblems. So I can see merge sort is flowing from top to bottom. So merge sort is top to bottom approach. Top to bottom approach. Now after getting, so this is one solution. This is another solution. This is third problem solution. This is fourth problem solution. Fifth problem solution. Sixth problem solution. Because we cannot divide those subproblems further. So only one element is there in all the subproblems. At the bottommost level or the leaf level. So whatever the subproblems we obtained finally, those subproblems cannot be divided further. Is it clear now? So each subproblem element is treated as a solution. Like that, irrespective of the elements, we say that these are the solutions. Suppose If we take this, what is first element? 2 is the first element. What is second element? 10 is the second element. What is the third element? 9 is the third element. What is the fourth element? 6 is the fourth element. What is fifth element? 5 is the fifth element. So 4 is the seventh element. So these are the solutions. So this problem is containing only one element. This problem is containing only one element. This problem. All the leaf level sub-problems are containing only one element problems. Is it clear now? So now at bottommost we got the solutions. But our target is calculating solution of 1:6. Calculating solution of 1:6. For calculating solution of 1:6, we must know 1:3 solution, 4:6 solution. For knowing 1:3 solution, we must know 1:2 solution and 3. That means we need to combine 1:2 and 3. Then only we get 1:3 solution. If we, after calculating 4:5 solution, if we combine 4:5 and 6:6, then only we get the solution. So merge is bottom to top. So we collect the solutions from the bottommost in the tree structure and merge all the solutions. So we say that merge is bottom to top. I will tell you. So which elements are going to be merged? Now 1:1 and 2:2 merged each other. Then only we get solution as 1:2. So first merge this. This means take these two elements first. First index number and second index number elements first. Suppose if we assume this is array A. Okay na? So this array A is divided into sub problems and so on like that. Okay na? But while merging these two elements, we need to have a separate flat form. So for that we are assuming another temporary array. The temporary array assumed as B. Okay? Then how we can merge the elements now? So merging is a separate procedure which is required in merge sort. We can merge these two elements by considering just by selecting first element in the first subproblem and first element in the second subproblem. We need to combine these two elements because all the elements are sorted. This is the solution of this problem and this is the solution of second subproblem. Then select first element in the first subproblem and first element in the second subproblem. Compare these two elements. Whichever is smaller, they copy that element into auxiliary array. We treat it as auxiliary array or temporary array. Auxiliary array. We are using this particular auxiliary array for sorting the elements, getting the sorted order list in auxiliary array because it is not possible getting the sorted array in original array. Okay na? Then compare this just by taking I and j. I is one variable which is used for selecting the elements from the first array and j is another variable which is used for selecting elements in the second array. So according to this tree structure, our ultimate aim is getting 1:2 solution. So 1:2 solution can be obtained by combining solution of 1:1 and solution of 2:2. So the solution of 1:1 is 2, solution of 2:2 is 10. Okay, then combine these two. So combine procedure is ultimately the combine procedure selects all the elements in the first array and all the elements in the second array, but one element at a time. We are going to compare the selected location elements. Whichever is smaller, we are going to copy that smaller element into auxiliary array and we need to increment that pointer by 1 unit, not second variable pointer because that is not yet copied. Okay, so compare this element a of I and a of j because array is a. So a of I is 2, a of j is 10. Then compare these two elements. A of I is smaller, then copy a of I into auxiliary array and increment I by 1 unit because only one element is there. It is crossed this boundary because this is mid. Mid is 1. Then it is crossed this boundary. Crossed boundary means it entered into second subproblem. Then stop comparing here because all the elements in the first subproblem are copied completely because only one element is there. We can observe this particular difference if more than one element is there. Okay, we will see just by combining all the problems. So whatever the remaining elements that are there in second subproblem, blindly copy remaining elements into auxiliary array and increment pointer by 1 unit. Only one element is there, 10. If you increment j by 1 unit, it crosses its boundary because its boundary is only 2. Its boundary is only 2. Then it crosses, it goes outside of the problem. Then after combining, again copy these two elements into original array. Then we get sorted order list as 2, 10. Next one is 9. Okay, now we got this solution. We got 1:2 solution, that is 2, 10. 1:2 solution is 2, 10. Then for getting 1:3, we need to combine 1:2 solution with 3:3. What is 3:3? 9. What is 1:2? 2, 10. 1:2 is 2, 10. And the third problem solution is 9. Again take temporary array, means auxiliary array with the same size as original array. Okay, na? Then same story. Take one variable at first subproblem in the first element in the first subproblem. take another element, it's another variable which is pointing first element in the second subproblem. One element should point first element in the first subproblem. One variable should point first element in the first subproblem. Another variable should point first element in the second subproblem. Then compare the location elements. A of I is 2, A of j is 9. A of I is 2, A of j is 9. Then A of I is smaller. Then copy A of I into auxiliary array and increment I by 1 unit, not incrementing j because j is not yet affected. Okay, na? Then compare A of I with A of j. Here A of j is smaller, then copy A of j into auxiliary array, then increment j by 1 unit. What is its boundary? 3 only. 3. Once you increment j by 1 unit, it crosses its boundary. Then all the elements are completely copied. Then whatever the remaining elements that are there, blindly copy those elements completely in the same order from the current location of I to last location. Its last location is 2 only. Then copy this element and increment I by 1 unit. What is I boundary? What is I boundary? 2 only. Then it is also crossed its boundary. Then we got this solution. 2, 9, 10 is the solution of first two subproblems. Then you got 2, 9, 10 is the solution of 1 is 2, 3. Okay, na? So here, while applying merge, we are supposed to consider one auxiliary array with the same size of original array for holding the temporary results. For holding the temporary results, by using that array, we can merge two selected subproblem solutions. We can merge two selected subproblem solutions. Now we got this problem solution completely. That solution is 2, 9, 10. Is it clear now? Okay, na? So after getting first subproblem solution, you are supposed to calculate 4:6. Then only after combining 1:3 and 4:6 solutions, we get original problem solution. Our target is getting the solution of 1:6, not individual problem solutions. Just by using this criteria, I got 1:3 solution. Then how can I get 4:6 solution? First calculate 4:5 solution and combine this 4:5 solution with 6:6. What is 4:5? What are 4:5? 6 is one element, 5 is another element, 4 is one element. But here we need to combine 4:5 first. 4:5 first. These two subproblems first. For obtaining 4:6. For obtaining 4:6, we are supposed to get 4:5 solution, combined solution. After getting 4:5, combine the solution with 6:6. Then only we get 4:6. Okay, na? So again, same. Take I here, j here. Then take B, auxiliary array B. Then compare A of I with A of j. Here A of j is smaller than A of I. Then copy A of I into auxiliary array. Increment j by 1 unit. What is its boundary? 5 is its boundary. Then it is crossed. Once you increment j by 1 unit, it's crossed its boundary. It crossed its boundary. Then whatever the remaining elements that are there in first subproblem, blindly copy those elements into auxiliary array because these two are sorted. This is the solution of first subproblem. This is the solution of second subproblem. Every time you are copying lower numbers into auxiliary array, then whatever the remaining elements in second subproblem, those are greater than this. So that's why blindly copy all the remaining elements into auxiliary array. Then increment I by 1 unit. I is also crossing its boundary. What is I value? I is 4 only. Once increment I by 1 unit, it crosses its boundary. Then this is the solution of 4:5. This is the solution of 4:5. How we got solution? 6, 5 and last element is 4. So 6 location number is 3. 5th location number is 4 and 5th location number is 5 and 4th location number is 6. Now I got 4:5 solution, that is 5,6. 4:5 solution is 5,6. But for getting 4:6, I must merge 4:5 solution and 6:6. What is 4:5 solution? 6, 5. What is 6th solution? 4. Now I am going to merge these two solutions. I am removing this. Okay. And again apply the same concept. Again apply the same concept here. Just by using that concept, I can merge these two elements, these two subproblems. After merging these two subproblems, I can get the second subproblem complete solution. Okay. So 5, 6 is this 4:5 solution, and the 6 subproblem solution is 4. Now I need to combine these two. Then only I get original problem solution 4:6. So for getting original problem solution 4:6, I need to combine solution of 4:5, this one and this one. Okay, na? Again take auxiliary array with the same size. Okay, na? Make it as D and start I value here and j value here. What is ith location? First element in the first subproblem. J initial location is first element in the second subproblem. Again compare a of I and a of j. Here I can increment I up to mid only. I can increment I up to mid because this subproblem mid is 5. Up to 5 I can increment. J can be incremented up to high only. I is 6. This location number is 6. Okay. Now compare a of I and a of j. Which is smaller? A of j is smaller. Then copy a of j into auxiliary array 4. A of j into auxiliary array. That a of j is 4. Then increment j by 1 unit. What is its boundary? 6 only. If increment j by 1 unit, j becomes 7. This is out of boundary. 7 is out of boundary. Then whatever the elements that are remained in another problem, because this is solution of the first subproblem, this is the solution of second subproblem, and these elements are also sorted, this element is also sorted. If one subproblem solution is completely copied, whatever the remaining elements that are there in second subproblem, which are obviously greater than the copied elements. So whatever the remaining elements in the second subproblem, start from the current location number, blindly copy all the elements into auxiliary array. Then at a of I, copy a of I into auxiliary array, increment I by 1 unit, copy a of I into auxiliary array, increment I by 1 unit. Then what will happen after copying 6? What is the boundary of first subproblem? 5 only. What is the boundary of first subproblem? 5 only. So after copying fifth location element also into auxiliary array, once you increment I by 1 unit, it crosses its boundary. Then all the elements in second subproblem is also copied. Then this is the solution of 4:6. So what is the solution of 4:6? 4, 5 and 6. So what we are doing now? Merge is performing bottom to top. We are selecting all the individual problem solutions and we are getting in intermediate results. 1:2 is one intermediate result, 1:3 is one intermediate result, 4:5 is one intermediate result, 4:6 is one intermediate result. So for getting that, I am requiring low, mid and high. Low is 1, mid is required because I can increment the first subproblem variable up to mid only, and high is required because I can increment second subproblem variable up to high only, because that is the boundary of second subproblem. But by using mid, I can reach first element in the second subproblem. How I can reach first element in the second subproblem? Once you know mid, just by incrementing mid by 1 unit, we get second subproblem low location number. There I can start a j value. Okay, na? So like this, I can get two subproblems. Just by applying last merge on these two elements, I can get the original problem solution. I will show you that also in this. So the same procedure we need to apply to combine the final two subproblem solutions. This is left subproblem solution, this is right subproblem solution. Same. Take I here and j here and compare a of I and a of j. Here a of I is smaller than a of j, then copy a of I into auxiliary array, increment I by 1 unit. Now compare a of I and a of j. Here a of j is smaller than a of I, then increment j by 1 unit and copy a of j. Again compare these two elements. 5 is small. A of j means 5 is smaller than 9, then copy 5 into auxiliary array and increment j by 1 unit. Again still 6 is smaller than 10, then copy 6 into auxiliary array and increment j by 1 unit. Here j gets outside because j crosses outside of boundary, because the boundaries are only 6. If you increment j once again, then j crosses its boundary. Then whatever the remaining elements that are there in next subproblem or another subproblem, blindly copy those two subproblems because all the copied elements are smaller than the remaining elements in the array, because both are sorted. This subproblem is sorted, this subproblem is sorted. Once any subproblem is completely copied into auxiliary array, blindly copy the remaining elements in the second subproblem from the current location of I or j. Sometimes this subproblem elements may be smaller than second subproblem. In that case, whatever the current location of j, from that location copy all the elements up to high. Here from this current location copy all the elements from high to mid, I location number to mid. Then copy 9 and increment I by 1 unit. Copy 10, increment I by 1 unit. What will happen if increment I by 1 unit? It crosses its boundary. Okay, I crosses its boundary. Then whatever the elements that are copied into auxiliary array, this is the solution. But our target is getting the solution in A. Then again take one loop and copy 1 by 1 element just by taking low and high. Initially take I as low, increment I by 1 unit until reaching high. Then copy all the elements into auxiliary main array. Okay, na? Like this, just just by taking one loop, I can copy all the elements by selecting one by one element in the auxiliary array and directly copy auxiliary array elements into main array. Okay, na? So in this way we can merge or combine the two sorted sub arrays. But what is merge sort now? I have already explained. What is merge sort? If low less than high means at least two elements must be there. If low less than high means we expect two elements minimum. If low is less than high, immediately calculate mid. Mid is low plus high by 2. Once after calculating mid, immediately I am getting two sub problems. One is from low to mid, another one is mid plus 1 to high. Apply med sort on this problem and med sort on this problem. After getting the solutions of these two, merge those two sub problem solutions. Here I have already told 3 pointers or 3 variables are required. One is low. Low is the low for the first sub problem. Another one is high. High is the high for the second sub problem. Then how can I find the first sub problem end and second sub problem starting? Just by mid. Just by mid, I can identify first sub problem end. This is first sub problem end. Once you know mid, just by adding 1 to mid, I can get the first location of the second sub problem. So like this, I can call merge sort on two sub problems, and I can also call merge on those two subproblems for combining those two subproblem solutions. Here I am going to write merge procedure, and I will explain how we can write a merge procedure, how a merge procedure can be applied on this. If you understood this, then merge is very easy. This is merge sort. I am going to write merge procedure, and I will also explain merge procedure now. Now I explain merge procedure. So I have already told merge procedure is requiring 3 parameters. One is low. This is the low for the first subproblem, and another one is high. High is the last location number of the second subproblem, and third one is mid. Just by using mid, I can find the boundary or the last location of the first subproblem, and just by using mid itself, I can reach second subproblem low location number, because second subproblem low location number is mid plus 1. Okay, na? First subproblem last location number is mid. So that's why I read 3 parameters only. Now, in merge procedure, now take the first subproblem and second subproblem. Suppose the first subproblem low is H. This is auxiliary array low. This is auxiliary array B. Array B, or lower letter or higher letter, you can take. And this is second subproblem or last location number. Okay, because this is required because we need to point out the initial location number of the first subproblem. And this is I is the initial location, it's an auxiliary array low location number. Okay, na? And J is mid plus 1. J you need to take J as mid plus 1, because J you are supposed to start J at first initial location number of the second subproblem. Okay, so H I started at low. This is the low of the first subproblem, and I also initialized the low location number for the auxiliary array, and I started J at the first element in the second subproblem. First element location of the second subproblem is mid plus 1. Okay, na? So here I can increment H up to mid only, because mid is the boundary of first subproblem, and I can increment G up to high only. High is the second subproblem limit. So I can initially start at H at mid, H at low, because that is the first location of first element of the first subproblem, and this is the first element of the second subproblem. Then I can increment the first variable or first array variable up to mid only. Then I can increment second array variable up to high only. But at each and every H location number and J location value, I am going to compare. So based on comparison result, either I am copying A of H into auxiliary array or A of J into auxiliary array based on this. Okay, na? So initially H is started at low. Obviously low is less than or equal to mid, and J is started at mid plus 1. Obviously initially J is less than or equal to high. Okay, na? After comparing A of H and A of J, this is the first element in the first array, this is the first element in the second array. If A of H is less than or equal to A of J, A of H is treated as either lesser value or equal value, then immediately copy A of H into auxiliary array in ith location. I initially started at low. Okay, na? Increment H by 1 unit, because we are incrementing whichever array element is copied, increment that particular array variable only. Okay, na? Then increment H by 1 unit. Otherwise, if it is false, means A of H is greater than A of J, then copy A of J into auxiliary array, copy A of J into auxiliary array, increment J by 1 unit. But for commonly increment I by 1 unit. This is the auxiliary array location number. Once after copying one element into auxiliary array, increment auxiliary array variable also by 1 unit. Common. This is common incrementation. If you don't write here, then you have to write I equal to I plus 1 here or I equal to I plus 1 here. Unnecessarily we need to repeat 2 times if you don't write here. So this is the common incrementation because we are copying only one element. Either element may be a of h or a of j. Only one element we are copying. That element is a of h or a of j. For that we need to increment I by 1 unit. So if you repeat this procedure like this, either first array may be completely copied or second array may be completely copied. We have already seen the example. If first array is completely copied, whatever the location number that is stopped, whatever the j location number that is currently there, from that particular location number until high, we need to copy all those elements in the same order because first array is already sorted, second array is already sorted. If first array elements are completely copied, we say that whatever the remaining elements in second array, those remaining elements are greater than all the copied elements. Now we check it. Suppose if h is greater than mid, from this we can conclude that the first array elements are completely copied into auxiliary array. Then start from the current jth location until high. Copy all the elements into auxiliary array, increment I by 100 because here we are taking for loop, then automatically the for loop increments j by 100. J initially started at current j location in the second subproblem and that j value will be incremented up to high only because second subproblem boundary is high. Then copy all the elements into auxiliary array. Kth element, k plus 1th element, k plus second element, so on high because k is initially started at j, current j location. Then increment k by 1 unit every time until high and copy all kth location elements into auxiliary array, increment auxiliary array element by location number by 1 unit because we must move to next empty cell in the auxiliary array. Otherwise, if it is false, then we say that second array is completely copied. If first array copied is false means second array is completely copied. Then start from the current location of h because h is considered in the first array for selecting the elements and j is considered for selecting the second array elements. Suppose if second array is completely copied, this is false means if second array is completely copied, then start loop from the current location of the h and we can increment h by 1 unit until reaching mid because first subproblem boundary is mid. So from the current location of first array element or first array variable, increment h by 1 unit until mid, copy all the elements in the same sequence into auxiliary array because all these elements have already sorted. If second array is completely copied, then blindly copy the remaining elements in the second array into auxiliary array because these elements are already sorted, and whatever the copied elements, those are less than the remaining elements in the first array, then copy all the elements into auxiliary array. Now we got the sorted order list in auxiliary array, but we are supposed to maintain sorted order list in A. How can we copy sorted order list into A? Sorted order list is there in B. Again take one loop, start from low to high, copy low into auxiliary main array, B of low plus 1 into main array, B of low plus 2 into main array until B of high. Copy all elements into main array from the auxiliary array. Like this we get sorted order array from the auxiliary array. So by using this merge procedure, I can merge all the subproblem solutions and finally I can get the original problem. But initially sorted array is there in auxiliary array. Just by using last for loop, I can copy all the auxiliary array elements into main array. So this is about merge procedure. Okay. Now I am going to explain time complexity in the next video. Thank you for watching my video. Thank you so much.